Hello, my name is Howard Penrose and I will be your narrator for this presentation. The evaluation of induction warming stator cores for coil removal was presented at the 2012 Institute of Electrical and Electronics Engineers International Symposium on Electrical Insulation held in San Juan, Puerto Rico. The abstract read, "Past methods for warming stators for mechanical coil removal included gas flame, oven warming, oil bath, and electric heaters. Independent studies, including the Canadian Electrical Association's Evaluation of Electric Motor Repair Procedures in 1995 and the U.S. Department of the Navy NAVSEA Motor Repair Manual, identify that these methods have no measurable impact on the core and the environment. An induction warming method has been introduced with the intention to improve coil removal times and environmental impact even further. The purpose of this paper is to compare gas flame to inductive warming and review warming times, post-strip core condition, and impact on the stator core on integral horsepower machines. Dr. Penrose is the Vice President of Engineering and Reliability Services for Dry-Cylinder Electric Motors, the Outreach Director for the Society for Maintenance and Reliability Professionals, the Web Editor-in-Chief for the IEEE Dielectrics and Electrical Insulation Society, and the President of Success by Design Publishing. The more commonly known method for warming stators as part of a mechanical stripping method is the use of gas or electric warming table. These tables provide a separation of the heat source and stator core to prevent any uncontrolled temperatures. The temperature is observed by the operator using either a contact or infrared thermometer, and the readiness for coil removal is determined manually by removing the coil head. The optimal method is to heat the insulating material by warming the stator core first and allowing the heat to move towards the bore of the stator. The use of an oven is also possible. However, most repair shop ovens are convection types, which result in further drying and hardening of the insulation system, which makes it more difficult to remove the coils. Coils are removed using mechanical puller. The preferred type is hydraulic, which results in more control versus pneumatic pullers. There are a variety of warming and pulling methods, such as this one above, which all require the coils to be warmed first. Several independent sources cite this mechanical approach as being both environmentally sound and having less impact on the core of the electric machine, such as the Canadian Electrical Association's Evaluation of Electric Motor Repair Procedures Guidebook, NAVSEA Technical Manual, Electric Machinery Repair, Volume 1, Electric Motor Shop Procedures Manual, and the eSource and Rocky Mountain Institute Drive Power Motor Repairs. Labor times are similar to traditional burn-off oven methods, and the total time from start to finish reduced by an average of 7 to 10 hours. Induction bearing warmers to warm the core and warm the insulation system have been in use since the 1980s for small stators. Within the past several years, control logic and methods for increasing the size of electric machines that can be stripped using induction warming have advanced. The newer systems resemble core loss testers with proprietary control strategies and temperature feedback. The purpose of this paper was to compare a gas warming stripping method and induction warming method. The comparison is to include times, core loss, types of stator and frame, and general observations. 6 stators were selected, varying in size from 3 horsepower to 45 kilowatt or approximately 60 horsepower. Frame sizes from 213T to 324 and from 2 to 6 pole machines. These were first core loss tested and checked for hot spots. They were then put through the induction warming process, monitored with an infrared camera as well as particular induction warmers thermal control, and the core losses rechecked after cool down. The same stators were then warmed with the gas method, core losses checked, and time noted. The core loss tester was a Lexico Model 2125E 480 volt 270 amp with a 30, 60, 90 volt and 2000, 1389 amp outputs with a published accuracy of plus or minus 0.25% of the reading in watts. The infrared camera was a Fluke TI-30 with a 250 degrees centigrade range. The core loss tester is supplied by a main transformer, and it was noted that the power supply fluctuated during different times of the day. For the purposes of this paper, the raw data taken from the core loss tester will be presented with error ranges. Ambient temperatures remained between 20 and 22 degrees centigrade throughout testing. The commercial core loss tester is set up to produce watts per pound measurements. A conversion factor of 1 watt per pound to 2.20462262 watts per kilogram was used to produce watts per kilogram for this paper. Target and actual flux are determined by the instrument software, as is the watts per pound output. The stators were warmed using the induction warming machine. In addition to the built-in sensors, the cores were monitored periodically with an infrared camera in order to observe heat distribution through the core, winding, and frame. This table shows the target temperatures, actual temperatures, frame temperatures, and time to temperature. The windings are checked to see if they are warm and pliable prior to removal. It was noted that core losses increased in 3 of the stators versus the other 3. In these cases, the controls were set above normal levels in order to see what effect improving the warming time further would have on the stator core losses. It is believed that the rapid temperature increase may have affected the interlaminar insulation, whereas the 3 normal heating times and settings resulted in improved core losses. Most likely this was caused by de-stressing the cores. A general observation was that the additional caution must be taken if hot spots are detected in the laminations during the preheating core loss test. If a significant or greater than 10 degrees centigrade hot spot is detected, the induction warming method must be applied at lower power levels and monitored closely if the hot spot cannot be cleared prior to warming. This is a post-induction warming infrared of the hot spot test on one of the stators following the core loss test. As noted, no hot spots were identified. A before and after check on the feet to determine possible stator distortion was also performed, and no perceived changes found, indicating that the mechanical properties of the stators were maintained. The gas warming method involves a source of gas burners and baffles to direct heated air towards the core of the stator. The stator is mounted vertically to act as a chimney, and it warms from the outer part of the core towards the bore and from the side closest to the warming source towards the top. The arrangement is similar regardless of the warming source other than convection oven heating. For this portion of the study, the stators used for induction warming were warmed using this method. The windings remained in the stators, the temperatures were monitored through the warming process, and the times observed. The stators were then core loss tested in order to observe any changes. It is noted that the losses have changed again, with only stator number 3 continuing to increase in losses. All others had a value less than or close to the original core loss. No hot spots were recorded resulting from this process. One of the very first production-related conclusions that can be noted from the comparison is that the time required to warm a stator for stripping is greatly reduced. However, forcing the warming process faster than recommended methods, such as the under 20-minute warming in this study, can have a negative effect on core loss and, as a result, motor efficiency. Even in these cases, the greatest increase noted was 3.9%, stator number 6, well under the no more than 20% allowable increase noted in the IEEE standard 1068 published in 2009. Improvements in core losses in the 3 stators that followed standard warming power levels for the machine used indicate that there is potential for improvements in efficiency as a result of the methodology. A future study will review the impact of multiple warming processes on a stator using this methodology in order to compare to a Canadian Electrical Association study performed in 1994. It was identified during the study that core loss measurements are critical in case the stator housing warms enough to allow the stator core to slip. This would be a standard in any stripping process and is worth noting when mechanical stripping methods are used. No stator core movement was identified during the study. While studies including the previously mentioned Canadian Electrical Association study identify the gas warming method as having no negative environmental impact, the induction warming method eliminates any of the low-level emissions that do exist in the older methodology. Both methods eliminate the larger amounts of greenhouse gases and particulate emission from standard methods or traditional methods such as the burn-off ovens. Outside of the study, stators on machines through 1.1 megawatt have been warmed for stripping using this method. It is expected that further development will allow continued expansion of the technology to much larger machines. Continued research, including a closer look at how quickly a stator may be warmed without negative impact, continues, including a correlation between the initial core loss and length of time to warm the stator. At this time, the only company that we are aware of that performs this kind of stripping method is Drysulker Electric Motors. You can contact Drysulker at www.drysulker.com. Thank you very much.